Let's continue. Uh, we already discussed the point defect. We already discussed the point defects, right? Point defects means the defect at the uh, at any point of this crystal structure, right? So these are the different type of point defects. You know, the different type of point defect is the vacancy, substitutional, interstitial, short key, Franklin, non-stoichiometry, and this color center and exciton. These are all the point defects. Okay. So after that we calculate the equilibrium defects, concentration calculation. We calculate this one, and after that we calculate the Schottky defect and whose equilibrium defect concentration, and then we calculate the Franklin defects calculation, and then the ionic mobility, ionic conductivity for the point defect calculation. Now we comes into the line defect. Line defects mean there is a line is absent within this structure. This is the line defect, and this is called the dislocation. There are various types of dislocation appears. This is due to strength the dislocation can appears. Again, these are the expression of the energies expression, and these are the two extreme point was appears, and these types of sleepy, and the this is the sleepy due to pulling of these two crystal. This sleep is will be originated, and this is the Frank rate mechanism will be can be possibility. This 1 2 3 this type of shapes can be originated, and after 4 to 5 you can see this aim and end point are joined, and the follow up this type of structure can be produces. Okay, and this is the twinkle when these two types of the plane, this is the one type plane and this is the two type plane is a line. This is called the twin plane. This is twin plane. This is twinking. This is called the twinking. These two planes are the common plane, that why this is a twinking. And the two dislocation type, first one is the edge dislocation. That's mean at the edge is shifted, and the vector representing the magnitude and the direction of the lattice displacement is called the Burger vector B. Okay, in this figure you can see, this is the edge dislocation. This is the total crystal structure in this dislocation appears, and at the edge dislocation can be shifted from the left to the right hand side due to appearing of the under the stress. If we apply stress, this dislocation shifted from the left side to middle, and then after that the right hand side. And then screw dislocation means if the back side is like that, but in the front side you can see this was the shifted. This shifting is slightly just like a screw. You can see the screw is like that, like that. So this is called as a screw dislocation. Okay, these are all the line dislocation, and you can see this is a three-dimension plane. Okay, this is the dislocation line. This is called dislocation line, and you can see this is the two possibilities of the dislocation in this region. And displacement of the slip of a plane crystal continuous screw dislocation of a slip plane of the plane which is sleepy. Slip means the this is the slip. This was the slip. In this slip plane the dislocation is like that. Okay, this is the dislocation of slip, and you can see this is the rotation of this type of, which was the perpendicular. You can see this is the same in the previous picture. This was not in the same. This total block was shifted, but here the total block is not shifted, but here the middle point is march out. So here you can see this line is march out in this direction. Okay, this line is marched in this direction, and you can see this is the structure of this internal is like that. Okay, stress field of the dislocation, this is the screw dislocation of a rotational or the cylindrical displacement. You can see this is a cylinder, but in this position there is a shift. That's mean if we take a paper and if we connect to end, this is the formation. But if we connect this as in the upper portion, there is a displacement. So this is like that. Okay. So this is like that. This is the screw dislocation in a cylindrical crystal. Okay, and this is the expression of the shear stress of this dislocation. The each for each dislocation, this energy per unit length is found be like that. This is the expression for this cylinder. Okay, this is for expression of the cylinder, or R1, R2 is the internal and external radius, and this value nearly to 4 pi, and this is the excess energy. Okay, and if we comes into the planar dislocation, so there is a three types of defect: point defect, line defect, and plane defect. So now we comes into the planar imperfection, that's mean planar defect. The planar defect mainly you can see in this figure, this within the liquid, this is one plane, two plane, this is a one plane, and you can see this is the grain because they are a some periodicity. This is the crystal portion, this is the crystal. Okay, and within the two grain, this is called grain, this is called, within the two grain there is a boundary. So this is a grain, this is a grain, this is a grain boundary, this is a grain boundary. Okay, this is a grain and this is also a grain, and between two grains there is a grain boundary. Okay, and this is grain boundary is the very useful, or this portion, this is the imperfection of the solid is very useful, because these two imperfections, sometimes it will help are the practical uses, sometimes it will be losses or the benefit, demerit, its demerit sometimes, because the plane if there is a plane defects, they are then the mechanical property sometimes hamper, and this will be very useful for engineer for making a structure of the constructional structure. You need to know the mechanical property, and you can see the mechanical property will be helpful if the structure is crystalline. For crystalline structure, mechanical property is the very strong. So that's why we need to know the structure or the dislocation. The plane dislocation is very dangerous for the mechanical property. For mechanical property, dislocation is reduction, or the crystalline defects if reduced, then the mechanical property will be effective. But in conductivity or the optical, there is a different story, right? So this is the topical view or low angle gain boundary. This is called low angle gain boundary is the view, and this is the optical micro linear boundary of the germanium single crystal when view in the phase transfer of the go direction. If you see in the go direction, then we can see this is the boundary like that. And dislocation of crystal in this growth whisker kind the kind of the crystal growth are discussed above can be laid the thin or long crystal wood ground in the single dislocation. This is called the whisker. When the dislocation is the single dislocation, this is called the whisker dislocation. uh, you can see this is the phase construction microscope of the spiral growth pattern of silicon carbide. This is a growth pattern. This is the crystal, this is the spiral growth pattern, this is the plane of the crystal. That's mean the atom are arranged in like that. Okay, this is a crystal structure, but this structure is like that. This is another. So this is a one grain, this is another grain, and in this region this is the grain boundary, this is the grain boundary, this is the grain boundary, right? So this is the optical microscope micrograph, this is the micrograph, this is the transmission electron microscope TEM, transmission electron microscope. Electron microscope. Why electron microscope? Because the wavelength of the light is nearly 4,000 to 8,000 Armstrong, but atomic size nearly to 1 Armstrong. So electron electron waves due to wavelength of moving wavelength in the moving electron is nearly to 1 Armstrong. That's why it is can be helpful to knowing the information of the crystal structure. So TEM is the tools by which we can inform the crystal structure, and this is the images you can see. Okay, and that's it. In the next class we will be discuss from the color center, which is the point defect and so on. Okay, so that's it. Thank you.